Well, welcome everybody. This is John Sarver, a GLREA board member, and thank you for attending. And I'd like to thank our sponsors, the State Department of Environment, Great Lakes and Energy, Eagle, Homeland Solar, Harvest Solar, Sri Energy, and Sumter Solar. And I think most of you are probably members, but if you're not, we would love to have you join the family, which you can do at our website at glrea.org. It's real easy to do. You can just join online. And please mute yourself until Richard has finished his presentation. And let me turn it over to John Richter, who's going to introduce tonight's program.
Good evening. We're here tonight to talk about virtual power plants, which gets a ton of press right out there. It's sort of one of the hot, shiny new objects in the news sphere of energy these days. And we really started this off with the challenge at our year-end, year-begin meeting in December from Chairman Scripps. Oh, now this is a problem. There we go. So first of all, definition, what's a virtual power plant? So the Department of Energy says it's a connected aggregation of distributed energy resource technologies, which offers deeper integration of renewables and demand flexibility, which in turn offers more Americans cleaner and more affordable power, and I might add more reliable. The aggregator could be the electric utility, but increasingly it's a third-party company that does the aggregation. And the utility has some sort of signal. They say, look, the grid's under stress. We're having trouble meeting demand. The VPP kicks in. It might reduce demand. It might feed power into the grid. It might do some of both. And it relieves the stress. This is the DOE's conception. I don't want to hang on this too long, but you've got residences down here with bidirectional EV chargers and on-site generation, EV chargers that can be maybe turned off during peak periods, smart water heaters, energy storage, industrial operations, smart thermostats, all these things that can respond to a signal from the VPP operator that in turn, was initiated generally by the utility. So at our year-end, year-begin meeting, Chairman Scripps was our speaker, and he ended his talk with a substantial discussion of virtual power plants. And his take was this. He said the electricity demand in the MISO region, right, that's the independent system operator that we're in, that includes Michigan and a number of other states, is expected to grow by 128 gigawatts by 2030. Now, that's just an astoundingly big number. I think the total electric generating capacity of Michigan is like 30 gigawatts, right? So it's huge. If you think of a gigawatt as, a Fermi nuclear power plant, right? I think it's 1.3. So he asked, how can utilities in the region add that much when building a traditional power plant takes a decade? Well, that's a challenge, all right. And then he noted VPPs can add capacity very quickly, and the DOE is predicting 80 to 100 gigawatts of virtual power plants by 2030. So in his mind, the answer to the capacity challenge, driven mostly by data centers, is virtual power plants. And he closed with this. He said, I'll close with a request. I ask you, talking to us, right, to bring your best ideas. What are the right metrics connected with those ideas? What additional obstacles are you seeing that can be folded into a performance-based approach to sweeping away the barriers that inhibit our ability to get the distributed energy resources onto the system that we're going to need? So we didn't dream this up. Chairman Scripps asked us for our ideas. And I would add to meeting the capacity challenge, it's the perfect balance to renewables, right? Wind and solar are the cheapest way to produce a kilowatt hour of electricity. Their primary downside is their output's variable and it's weather dependent, right? VPP is the perfect partner for that because they are called to action when there's a shortfall in net capacity, right? All the brouhaha about small modular reactors, they can't do that. They might provide some marvelous baseload power, 24 hours a day, 365 days a year. The data centers certainly like that, but it doesn't balance renewables. So VPPs actually enable deeper renewable penetration, which is what we're all about. So what was our solution to Chairman Scripps' challenge? Well, we found an expert. So we recruited Richard Boehnke, who is with us here tonight as an expert witness in MPSC cases, to advocate for effective virtual power plant design, which he knows how to do because he has industry experience in setting up VPPs, which is actually quite rare. He also understands how regulated utilities have these odd profit incentives that make them behave very strangely. And so he understands their motivations. And with that, I'd like to hand it off to Richard to tell us about virtual power plants.
Thanks, John. Can everybody see my screen? Can I just get a thumbs up? All right. So as John said, I'm here to talk to you about virtual power plants. And before I get started, on that front, just want to say a little bit about my background. So most of this work that I'm going to be showing you tonight comes from my experience as the Director of Demand FLEXmarkets at Recurve, where I led the design and implementation and planning of virtual power plants in California. Where we deployed, went from $0 to $35 million in total system benefits flowing through our systems in less than 2 years. I also have master's degrees from TU Delft in sustainable energy technology and science and engineering. So what we're going to talk through tonight is focused on, of course, VPPs. But first, I'm going to talk a little bit about the electricity grid and how it currently works and how it's currently imagined. This may be review for many of you, but I think it's important to baseline before going forward into, well, what are these new systems that we could aggregate together? Then we'll talk about VPPs, what they are, what their role could be, and how they could impact you. And finally, thinking about, well, where do we get started with all this? How do we enable VPPs in Michigan answering Commissioner Scripps' challenge? So first, the electricity grid. Most of us see it every day and don't think anything of it, right? We see power lines down the roads coming to our houses and we plug in and we don't notice the electricity grid until it honestly fails, right? And we don't typically think about how it's structured. So this way of planning originated in the 20th century when things were set up, right? You have centralized utility control with this top-down infrastructure going from generation all the way to end users, and it's typically one direction, right? The power plants are generating and dispersing out. And you have these utility-owned assets that are monopoly controlled because it was imagined that in order to get us the systems that we need, we have to have these government-sanctioned monopolies because it's so expensive to get things moving. However, today, there are some added challenges that this 20th century thinking doesn't accommodate. One, as John mentioned earlier, we are adding wind and solar, which means we're adding uncontrollable supply to our generation mix. In addition, we have inconsistent demand. All of us are using electricity in new and varied ways all the time and at different times of the day. So it's much harder to forecast that demand. And as we're consistently adding more load, it gets more difficult to achieve that through this centralized model. So how does it work? And I'm just going to give you a relatively straightforward metaphor for how the grid works. So right now, we are supplied by a teeter-totter, not a water tower. And what I mean by that is we don't have a storage facility on the grid typically. So when you plug in your lamp or your toaster or turn on your microwave, that doesn't just siphon off a little bit of power out of the nebulous grid and then power your device. That power actually directly impacts the generation facilities that are pushing electrons to your home. So what we actually have is this massive teeter-totter balanced on a microsecond level basis of load and supply. And that balance must be maintained in order for the grid to function. And if it is not maintained, it causes problems. What I'm showing you now is just to give you an idea of the swings of load that we're seeing in MISO. So John mentioned that MISO is expecting substantial load growth over the next 5 years, but what does that really mean? So this is a screen grab from the MISO operations display. So that's the Mid-Continent Independent Service Operator. It serves 15 states, including Michigan, and roughly 45 million people. And what it's showing here is the actual load relative to what was forecast. And you can see the actual load. I took this at around 10 a.m. this morning, so we don't have the rest of the day, but you'll see that yellow line if you go to the website growing. But what you can see here is that from about 3 a.m., where you're getting the valley of load of, say, between 70 and 75 gigawatts, to the peak in the evening or late afternoon, early evening, we're having fluctuations of roughly 30 to 40 gigawatts of assets ramping up and then ramping down every day. And this is just a normal day. And what that shows is with these consistent fluctuations, we have a substantial amount of infrastructure that is not consistently used. It must fluctuate its operation throughout the day. And so when we're talking about adding peak load, we're talking about data centers and all these things that the utilities are really channeling concern about. We're actually talking about peak load. DTE is considering up to 7 gigawatts of load from data centers. Consumers is committed to adding 1 gigawatt. But what we see from that MISO operations display, and this would be consistent in Michigan, is we have these swings every day. And we have that inconsistent usage that then could be used as capacity if we could shift load into those off-peak times. Now, utilities are mandated to deliver service and mandated to be able to deliver at peak hours. And what peak hours are beyond just the daily peaks, there are going to be spikes throughout the year where load skyrockets and utilities are required to accommodate that. And those peak hours are roughly 40 to 80 hours a year. This is a graph. I know it's not from MISO, but I really appreciated it from PJM. And it's showing, as you can see, the dollar per megawatt hour for 2 years, one after the other. So you're looking at 2020 in blue and in brown 2021. And why I think this is important is it shows the incredible price volatility per megawatt hour at different times in the year. And you can see this dramatic spike in, say, late February, early March of 2021 that shows, wow, demand skyrocketed. And the utilities had to price electricity accordingly in order to deal with this. Now, with everyone talking about adding substantial load in the next 5 years, the current and persistent idea of how to deal with this, how to accommodate this new load, is by building gas peaker plants. Now, looking at the costs of this, ignoring for a moment the emissions or other challenges, right now the costs are projected, and these numbers come from the CEO of NextEra that build these sorts of power plants, roughly $2.4 billion for a gigawatt of construction. Not only that, you'd have millions of dollars annually for fixed costs just for maintaining the facility, and it would take roughly 10 years to build it. Not only that, we'd be building these pieces of infrastructure to be sitting dormant 8,700 hours a year. Just sitting there, waiting for those peak 40 to 80 hours to happen for it to be turned on and be delivering power. But with that idea and seeing there are so many more ways that we could manage our grid, it's time to start asking what's really important here. Are we talking about total energy that we care, that matters, or is it really peak that we care about? And then furthermore, what do we need to do to solve this problem without building these immense stranded assets? This is a chart from a paper that I would highly recommend everybody read, or at least the executive summary. The paper's title is Rethinking Load Growth, Assessing the Potential for Integration of Large Flexible Loads in U.S. Power Systems. And this paper is a phenomenal primer onto the state of our grid as it is today and what we could do to potentially add load without building substantial infrastructure. So what you're looking at here is a portion of this figure that you'll see in the paper, but on the right in the legend, you'll see the teal line, which says load addition at 1% curtailment. So what that's saying is, how much load could we add to each of these ISOs if that load was able to curtail for 80 hours a year, 1% of the year? In addition, this isn't looking at 80 hours straight. These load curtailment events would happen roughly in 2-hour chunks. And what this paper analyzed and found is that with 1% flexibility, you could add almost 19 gigawatts of power to the MISO grid without building additional infrastructure to accommodate it. That's a substantial amount of load to add without needing more power plants, without needing more infrastructure or transmission. It's incredible. And what this paper really pushes me to do, and I think should push everybody in this space, is to think about, where can we find additional value in flexibility on the grid? And thinking about, what resources do we have or could we put in place that we're not currently tapping? And this brings us to virtual power plants. And as John mentioned earlier, you stole my thunder. The DOE defines a virtual power plant as a connected aggregation of distributed energy resource technologies. But what I want you to take from that is, there are multiple ways to imagine delivering the same services, right? The grid, in one sense, yes, the grid is a flow of electrons. In another sense, the grid is facilitating the delivery of services. We want to cool our homes. We want to heat our food. We want to wash our clothes, right? We may not need to push more electrons to do those things. So the 20th century imagination says, well, let's just build billions of dollars of centralized power plants to accommodate those peak times of 40 hours a year. However, we could also imagine doing this using existing and new decentralized resources to reduce, shift, and shed load. Now, what am I talking about? And John said this earlier, but just to say again, what resources are we considering? Now, this could be your solar panels or your electric vehicle or your battery in your home, but you could also aggregate heat pumps, smart thermostats, water heaters, even home insulation. The idea here is, we're aggregating resources that can impact energy demand or supply at the point of use. And what would a virtual power plant do? How do these aggregations impact the grid? Really, it's in 3 ways, and VPPs do all 3 of these. First, you can reduce load, and this is persistently. So thinking energy efficiency, so you put in more efficient light bulbs or home insulation, or your local production. So this could be your solar panels, where you install this system and it immediately lowers the energy consumption at your home or facility. Next, you could shift load. So this is saying, rather than using at peak times, I'm going to use before or after the peak to limit my exposure or to limit demand at those high cost times. And this could be done using energy storage. And I mean this more broadly than just batteries. You could preheat or cool your home or your water, right? These are technologies that can have dramatic impacts. You could also use battery storage or your EV charging. And finally, you could shed load. So this is when a utility would call an event saying, hey, turn off your devices. And then end users, or right now it's typically factories, will have a great impact where they will turn off their manufacturing for a certain number of hours. And what this looks like on the example of an actual day is, you have these decentralized assets being able to deliver flexibility in the grid. And not only does it impact your local grid, it also provides the potential for additional value streams for ratepayers, because if you're selling flexibility, then you could be compensated for that flexibility. So in this example on the right, this chart, you have in this black line, the net load, right? Where you're seeing, okay, we're traveling down here throughout the day, and for whatever reason, the utility couldn't handle this peak beyond the 3.25 gigawatts. So they called in the VPP. And so this projected load that was to happen in the evening got shifted throughout the day. And so then what would happen is you have all of these different assets now fall under this net load, this dotted orange line, going below what the utility could forecast as a peak. And so in order to imagine, like, what is the grid of the 21st century, the way I like to think about it, and the way that I think is relatively straightforward, is thinking about the grid as similar to the internet, where you have your internet service providers that are maintaining the wires and keeping things connected. But then you also have companies and software and apps that are built on top of the internet, and whole businesses are run on top of the system using it, as opposed to just the internet as one amalgamated monopoly. So that's what VPPs allow to happen. And just to be clear, these things are happening now. It's not just an idea or a thought experiment. Virtual power plants are having a renaissance right now. And what's fascinating is all of these examples are just from the past 2 months. And it seems that every week there's another article published about another virtual power plant breaking another record of how much they're deploying to the grid. So just last week, you had a test in California of a virtual power plant in PG&E that delivered 100,000 batteries and 535 megawatts of power to the grid. In Puerto Rico in July, you had 70,000 batteries preventing multiple load shedding events, so read blackouts. In Sunrun, deploying 340 megawatts, and New England deploying 375. All of these things are happening right now, and we need to find ways to engage our policymakers and regulators to enact the decisions that facilitate these to happen. So what are the impacts? Where could this go? Now, what we're looking at, and this is the DOE, saying that over the next 5 years, VPPs could have a 10 to 20% peak load reduction, saving it up to $10 billion in annual grid costs. That's an immense figure. Now, another study that came out of the Brattle Group, they're associated with Google, found that VPPs can be as reliable as conventional sources and also can save billions of dollars in infrastructure costs if implemented. Further, they can provide billions of dollars in additional societal benefits beyond generation avoidance or infrastructure upgrades. And how this would impact us? Well, first, we would have a modernized grid that's built not only on these centralized assets, but also on distributed assets, providing flexibility and using the existing infrastructure to a fuller extent. What that would do is limit investments in generation, transmission, and distribution, which are costly and take significant amounts of time to build. And building this sort of system provides greater resilience. You have on-bill savings due to not investing in these costly technologies, and the potential of additional value of providing capacity back to the grid. And in certain cases, that would mean different tariffs on your utility bill, or even value getting paid back to you, depending on how these systems were designed. Now, what could this look like in Michigan right now? Just a thought experiment. Right now in Michigan, there are roughly 100,000 batteries driving around that plug in. So there are roughly 83,000 fully electric vehicles and roughly 17,000 plug-in hybrids. This accounts for roughly 6.5 gigawatt hours of storage, which is massive. Now, if you installed a relatively cheap bidirectional charger that had a 11.5 kilowatt power rating, This would translate, with a few safety factors involved, to roughly 575 megawatts of deployable storage with 1.6 gigawatt hours of storage capacity available today. Now, for the sense of comparison, currently in 2025, the planning resource auction for MISO, read 15 states, bid in roughly 0.5 gigawatts of battery storage. So if we were to enable just the electric vehicles in Michigan today, we would eclipse what was bid into the PRA and MISO for 2025. And I just find that fascinating. Now, John already mentioned the call to action from Chairman Scripps, and what we're doing is bringing those strategies that are required to enable VPPs in Michigan. Fundamentally, this is something that we can do, and we as ratepayers need to continue to push our regulators and our policymakers to adopt policies that allow VPPs to be developed and innovations to be born. Because right now, we don't have significant utility leadership in the state. And MISO is also dragging its feet on allowing VPPs to bid into wholesale markets. Excuse me. And what that means is we have a huge opportunity for our regulators and policymakers to take the lead. And as ratepayers and voters, we have the capability to influence them, to reduce our costs and provide additional value streams. So finally, where do we get started and what can we do? In order to unlock this innovative approach and build the grid of the 21st century, we need to unlock first an understanding of the costs per marginal megawatt hour and the data that comes along with it. So according to the DOE, for VPPs to drive down electricity bills, we must also address system integration. Not in the sense of how we use power, but when we use it. Right now, power and energy are time-valued resources. They're not flat anymore. A kilowatt hour used at noon costs a very different amount than a kilowatt hour used at 7 p.m. What you're looking at here on the left is the sum of the total resource cost benefits from California. Now, this was work that was done at Recurve. It's public now, and these avoided cost data are public in California. And why that's important is this shows per hour of the day, per month of the year, the sum of the TRC benefits. And what you can see with this heat map is the total benefits are very localized to very few hours in the year. Now, if we were able to do this work in Michigan, it would look very different because we have winter peaks, and that would change the calculus. However, in order to unlock the market, we need to know what the value of the resource is that we're trading on. So here are the three things that I see from my experience that we need to enable in Michigan to drive this home. First, we need to define the resource we're trading. We need to think about creating the metric system, right? As opposed to everybody using their elbow to their end of their ring finger as a cubit, or excuse me, middle finger as a cubit. Everybody can't use a different length. We must have a standard of weights and measures that's transparent, that allows anybody to calculate the value and get the same answer. Now, what I mean by standard of weights and measures, it's first, what level are we measuring? Are we measuring at the whole building or at the device level? Or is it different for different devices? So for example, measuring energy efficiency is more different than measuring batteries. Batteries have their own meter attached directly to them. So we need that sort of rule, and we need to make that system transparent and auditable so it can become a financial mechanism. Further, ideally, this would be a national standard, or at least building towards a national standard. So innovative companies could copy paste things that are working in one state and bring them to another. Second, we need to value this resource that we want to trade. Now, my argument is that this should be tied to the utility avoided costs. Why? Because if we're reducing the cost, right, or we're providing benefits at a certain rate, well, we should value those, I say, well, negative watts at the rate at which they would cost. So what this would do is create a reliable, robust value stream that companies could assess, find where their business model could provide value, and then start selling that value. Further, utilities are already calculating the marginal cost per megawatt hour per year projected out for 20, 30, perhaps even more years, because they need to know this for their infrastructure planning. Finally, we need to create a mechanism to trade, meaning you need a market. You need some way to enable the buying and selling of this resource. And just to drive it home, why this is important is because these things are happening today. They're not happening next year. They're not happening 10 years from now. These technologies and aggregations are happening now, and we need to bring them to Michigan to accommodate the load growth that's being projected at rates that don't involve building large, expensive, stranded assets that are centralized, controlled. So what's the goal? We want to, rather than build these big power plants, we want to invest in ratepayers and create a synergetic system that's reliable and meets our needs at a fraction of the cost. Thank you.
And with that, we're open to questions. Hopefully this has stimulated a great deal of thought in our participants. And, we have this expert here. Now is the time to ask. Mercy, you're on mute.
I'd like to make a comment. 30 years ago, when I lived in Washington, D.C., I had air conditioning. I don't have it here now, but and the electric company offered a system whereby they could turn my unit, my electrical air conditioning system off when the peak got too hard. They didn't have enough. They didn't have enough electricity to send for people who wanted it, and I did that. And they gave me a discount on my electric bill, and it worked fine. I never had to worry about it. I mean, it just was something that they installed in my outdoor, heat exchanger. So,
Both
is
DTE
that
and
what you're talking about? That type of thing?
So
Richard, let me start and I'll let you run with that. So both DTE and consumers have programs like that here to interrupt air conditioning in Michigan. DTE's program is in a shambles because the device that shuts off the air conditioner when they signal it doesn't work in 40% of the homes. But the people are still getting the discount. And in many cases, the reason it doesn't work is because the homeowner has pulled the cord on it so it doesn't have power. So it won't turn off the air conditioner, but they still get the discount. So that's the first part of your question. But
I never did that to mine.
So the question of, is this what you're talking about? I'll let Richard answer that one.
Yeah, and thank you for the question. And it is in part what we're talking about, right? It's part of this greater aggregation that we can bring to bear on the grid. So absolutely, you're thinking in the right way.
I have a addition to that.
Sure.
In the early 90s, I was rebuilding a home. This is in Livingston County, where DTE had a water heater controller, electric water heater controller, that they said they could control on off during peak times. One thing that I noticed, because I was rebuilding the house at that time, was I would connect it up, have them inspect it, and their technician would disconnect it. It's a little round box about the size of a meter, and I went through that 2 or 3 times, and finally I just said, okay, we'll leave it disconnected. But anyway, right along what Marcia was talking about.
And if I may add one thing to this, is one of the significant differences between the aggregations into a virtual power plant that I'm discussing versus these sorts of programs that already exist. One of the significant differences is how savings are measured. So right now, the vast majority of energy programs that come through utilities, this is not just in Michigan, but nationally, are suffering from deemed savings, meaning when a light bulb gets installed or a controller gets installed on your water heater, the utility is able to claim without any metering a certain level of impact. And so this sort of system requires measurement. It requires verification because you're not being paid at the onset for doing nothing. You're being paid for what you actually deliver, similar to how a power plant would be paid, right? They're paid for what they can deliver.
Makes perfect sense.
Yes, it does.
Come on. John, you're on mute.
Sorry, yes, Nikki, you're up. And you're on mute.
I'm on mute. I had two questions, really. One is you were talking about EVs being bidirectional. Are all EVs would be capable? Because like I have an old Bolt, would that be capable of being bidirectional? That's my first question. And the second question is, we already generate electricity to the system through the solar panels. So if they have a call, how does that work? How do they differentiate what they're getting from the new VPP versus what they would normally be getting from my solar panels?
Nikki, that's a great question, or great two questions. And I have partial answers for both, but this would require me to look into specific technologies. So first, are all EVs capable? I don't know all the EV battery systems, but what I do know is that EV chargers are either unidirectional or bidirectional. And typically the single direction chargers are cheaper, and that's what on average is installed in the States. So regardless of if your vehicle is capable, that's something different, but I doubt your charger, if it's the one you got several years ago, has the capability to export energy back to either your home or to the grid. Then thinking about you're already generating electricity and how would it work to be aggregated into a VPP, the hard answer is it would depend. So right now, since we don't have VPPs in Michigan, how those systems would be aggregated and then what, oh, thank you, John. Appreciate that. Nikki, if you look in the chat, John mentioned that not all EVs have bidirectional capabilities. Thank you, I wasn't aware of that. But depending on how the VPP is designed and who's running it, so theoretically you could have either utilities running a VPP and they have their own structure, or you have third-party aggregators running VPPs and they would have their own. And so what we would need to do is first allow these systems to happen, and then they would aggregate the assets and then provide you an offer because you have assets that could bid into the system, right? And so what you would want to do is, well, what's the best offer? What can you get either the most savings or where you're getting more value? But I think the short answer is having solar panels is fantastic, and having an EV, even if it's only one direction, can be useful. It would just regulate when you're charging relative to not. So how about
All right, Harvey, you're up.
Okay, so
John, don't forget Stephen too.
Oh, I'm not seeing him, so my
yeah.
bad.
So Stephen, you're next. You're on deck.
okay.
Hello, Harvey.
Hi. So my understanding is that currently DTE is paid a guaranteed return on their capital investment. It seems to me their incentive is to resist this as hard as possible and to instead want to build as many big, expensive gas peaker plants as they can. How do we change that? How do we fix the incentives so that not only are we forcing them to do that, but maybe that they want to do the VPP thing?
Yeah, Harvey, that is honestly, that's probably the hardest part of engaging these systems in the US is you have this split incentive where utilities don't want to do it. So first, I think it's finding areas where utilities could rate base capital investments that would enable VPPs. So we could think about data, we could think about software, and things that would then enable them to at least have some cost recovery. But fundamentally, we would be reducing the cost of capital. We'd be reducing the cost of investments. One other piece that I would like to share, and I know that a few of you have read my utility dive article, but in this example of electric vehicles, rather than rate basing a 1 gigawatt power plant, we could rate base 100,000 EVs and bidirectional chargers, right? So then the utility could have a guaranteed return on that cost of capital. It's just that those 100,000 EVs and bidirectional chargers could be installed across the state and essentially given to individuals where they're needed most. And so there could be mechanisms where we could create or reimagine a way of delivering a return on investment, but it's going to be challenging. And I think that rather than sugarcoating it, I think that's, you've hit the nail on the head. And finding ways to reimagine it, that's the goal.
I have a comment I'd like to make about that, if I may. It's that we have in the state, as you probably know, a number of co-op electric companies and co-ops and also city-owned. And so I think in those areas, we could probably make a real dent in this approach because they would be freer to make the turn. Maybe I'm wrong about that, but it seems to me as though that would be, they don't always have a lot of capital investment. That's what I'm saying.
All right, Stephen, you've had your hand up for a good long time, and then we'll do John and then Nick.
Yes. Hey, folks. Solar Steve's back. Topic very near and dear to my heart. Thank you, Richard. Kind of covered my questions, but I'm gonna free flow here for a second. First of all, on incentives, Hermann Scheer, the father of the feed-in tariff and what really sparked the green energy revolution in Germany, he has some great books and content out there. And one of his sayings that kind of stuck with me was, we've given the control and decisions to the only party that has an incentive to delay the energy transition, i.e. the utilities with their centralized infrastructure, their fossil fuel supply chains, etc. So just to start with a heavy hitter, that one. Back to incentives locally or close to home. DT makes an annual gross profit of over $6 billion, investing in those costly investments of generation, transmission, and distribution you exactly were talking about. So I'm kind of repeating, it is a clear misaligned incentive, if you ask me. As far as just boots on the ground, I'm an installer of these advanced systems, including bidirectional EV chargers, which is just at their tip of the spear, if you will, at least in the US. And I'll say we have a very long ways to go. Trying to interconnect even a basic solar PV plus energy storage system to the distribution grid, it's a major fight. So I know those are comments, I guess, to get a question out there. You mentioned relatively cheap bidirectional chargers. I don't know of any that are relatively cheap. We mentioned Ford, Tesla has it with the Cybertruck now, and then the only generic one I know about is Point Guard, which is a battery system, not an OEM. So just curious if you can comment on, I guess, general incentives a little bit more, and then specifically those relatively cheap bidirectional chargers.
Yeah, Stephen, let me get back to you on the name. I was referencing something from my utility dive article, and I'll send you the link once I get there. But there's a bidirectional charger that had a 11.5 kilowatt rating that I believe was projected installed of about $5,000, but not prevalent in the US. So let me put your email in the chat, and I'd love to get back to you on that. All right, John.
Yeah, a virtual power plant, right, could be like a microgrid that's maybe got solar and batteries and other distributed energy resources. Or it could, right, be a private company that has arrangements with 1,000 hot water heaters that they can kind of turn off if needed. And I'm just wondering if, I assume those are both would be considered virtual power plants. Is one of them more important or more valuable than the other?
At first blush, I'm not entirely certain how to answer that, John. The way I'd evaluate the value of a virtual power plant is how much it could reduce peak, right? These aggregations are impactful because they can shift load away from peak. Fundamentally, that's where the highest cost electricity is, and thus the highest value to reduce. So regardless of if it's 1,000 water heaters or 20,000 heat pumps or 100,000 batteries, it's how are you impacting peak, and then how are you being remunerated for that value. So that's the way I'd look at things, and think that it's also really important to look at things specifically when considering retrofits that reduce the usage as opposed to provide shifting. So, more efficient equipment, for example, because if you're making a household or you're making a business more efficient at noon when solar's active, nobody cares. Right now in California, in the middle of the summer at noon, they have negative energy prices because there's enough solar on the grid that they're paying other states to take it. Whereas 7 hours later, you can have significant energy costs, right? And so we need to find, this is where utility data is really important, is we need to be able to find not only the value in the costs, right? So which hours of the day matter. We also need to be able to find those users that are causing problems or causing challenges, and then be able to serve them directly and target them for specific retrofits that would reduce their load in those peak times, right? So I think that's a lot. Sorry for just expounding on that for a moment, but I think that's where it's really important when thinking about how to enable virtual power plants and how to enable these aggregations, rather than thinking about what specific technology is the best. What my goal is to implement and work on the policy and regulatory side is how do we create the conditions where all technologies that are not carbon intensive can participate, right? If we have a standard of weights and measures and we have a standard of value, then we can trade on the resource. And so if we allow that to happen, then whatever technologies come in and can provide those reductions that are measured, well, then they can participate.
Well, yeah, it seems like the basic premise then is geography is not as important as the time element, because the time element is the key to the peak prices. But let me ask you kind of a follow-up question: do the virtual power plants potentially go into both the distribution system or at the transmission level, or is it more likely transmission or distribution, or just depends?
Right. Okay, so first, geography is important. I just want to make sure to not ignore that really quickly, because there are certain places in Michigan that experience blackouts and outages far more than others. And so we need to think not only time-based, but geographically based on who's being served or not being served. And then thinking about the distribution system versus the transmission system, this is where I see a challenge in the current state of affairs. I don't know if folks are aware of FERC 2222, which was a policy enacted that enabled the aggregation of assets to be bid onto the transmission system. Where that falls short in my eyes is, well, the impacts that we're aggregating might not be bid, right? They might be negative impacts, right? We might just be reducing demand as opposed to producing power and putting it up into the transmission system. So I think the answer is yes to it, like where there will be impact, and there's more work to be done to capitalize on all of that impact. All right, Nick, I think you were next, and then we'll go to Patrick, and then I guess John, and then back to Stephen.
Thanks, Richard. I appreciate you going into detail here, and I thought you did a really nice job of outlining some of the challenges. And you mentioned three in particular. One was defining the actual units used. The second was valuing them, and then the third is like finding a way to actually make this transaction happen. And I know that virtual power plants are a big deal. You gave some examples of this happening in other places. And so it looks like other groups have solved these problems. These groups are out there making power purchase agreements with utilities. And so what is it about the Michigan system that's preventing these from taking place here? And I have a follow-up question for you if we have time.
Sure. So I'll give you just a quick answer. Right now, these aggregations are not allowed in MISO. And then the utilities are also dragging their feet because MISO is dragging its feet. So what we need to do is we need to make sure that VPPs and aggregated resources are available to be bid onto the wholesale markets and transmission side. And then we need the utilities to move. And so that's where I'd start.
So who at MISO can we write letters to say, hey, enable VPPs?
I'd turn this over to one of the several Johns on the call. And John Freeman, I see you just came off mute if you want to hop in.
Well, I just have a follow-up question.
Yeah.
So is California implementing a virtual power plant? So their MISO, whatever MISO they're applying.
CAISO. Yeah.
CAISO. So one CAISO can say yes to virtual power plants, but a PG&M or a MISO can say no to it. There's no uniform standard across the country.
So FERC 2222 was a policy enacted, and the rollout and implementation of that policy is different for the ISOs. Yes.
Okay, thank you. Let's get back to Patrick or Nick.
We can talk later. Nick, are we good? Can we go on to Patrick or?
I guess one last question. So if we needed to lobby within MISO to get this to happen, or if, say, I wanted to propose a power purchase agreement to a utility, who are the roles that I need to talk to? If I wanted to go out and actually make a difference, who do I need to talk to? Who do I need to support in order to make this change happen for Michigan?
Yeah, quite frankly, I don't have a firm answer for you right now. Where I'm focusing and what we're doing with GLREA is right now focusing on the rate cases. And then the next iteration is focusing to get these sorts of data enabled with the next integrated resource plans of the utilities. The reason we're focusing here is one, focusing local, you can have a greater impact. Your voice matters in Michigan, both as a ratepayer and as a voter. And so that to me is really crucial, because if we can enable the transparency in cost and we can enable transparency in data, then what we can do is put additional pressure on the utilities, because we can say, hey, you are not acting in ratepayers' best interests. Here's the cost that you're generating beyond what is reasonable, and we can show it. And I think to me, that's that's my theory of change for this, because acting at the level, higher with MISO, right, governing the 15 states, they are going through a process to implement Order for 2222, but the timeline of that is they originally, I think, wanted 2030. There's been pushback to try and make it sooner. But my theory of change and why I'm excited to do this work here is I think we can have a direct impact in Michigan and create the ability for these aggregations to have an impact. And then once that ability is there, you can show the value. Once you can show the value, utilities don't have the same defense, right? They can't say, oh, it won't work. It's like, nope, it works around the country and it's more cost effective to ratepayers. So then the Public Services Commission will have the ability to mandate different changes.
And just to clarify, when you said you're working on rate cases, that's an estimate of the amount, the costs essentially of installing one of these VPPs and having it run, so that then you could go to the Public Utilities Commission and show them that this is cost effective.
Right now, actually, it's a step before that. It's making sure that we have avoided cost data, that we have access to utility data to understand what the value of these systems could be for ratepayers in Michigan. Because right now, making an assessment of that value is very challenging.
Gotcha. Well, I have some ideas on how to do that, and I know Steve does as well. I've chatted with him a couple of times, so I might drop into your email at some point with some ideas.
I would love that. Please do.
Cool. Thank you.
If I could try and answer part of Nick's question, MISO has a 2222 implementation plan. It has been adjudicated and sued and fought about for years. I don't think we're going to move that boat. However, that's for bidding VPP or aggregated resources into the transmission network. Most of the opportunity is not there. It's in the distribution network, and that is firmly under the purview of the Public Service Commission and the state legislature. The Public Service Commission currently allows aggregation, but only for customers with peak demand of more than a megawatt, which should be, a fairly large user, right? And they specifically prohibit aggregations for smaller users. They're waiting for their staff to create customer protection plan, which staff is dragging their feet on. And so that's why we're going at the MPSC, right? So for the kinds of things Richard's talking about, where it's distribution connected things, reducing demand, or EV batteries, or all that's on the distribution system. We can do that at the state level and don't have to wait for MISO.
That's awesome news, John. And just to clarify there, that means that I can use the existing grid to connect a VPP to, say, a factory in Detroit. And since it's not going through major transmission systems, then I could do a power purchase agreement with the factory in Detroit and skip all of the FERC requirements that MISO might be in the way of.
In theory, I don't know if any Michigan customers have done this or how it works, right? It's kind of a mystery at this point. That's one of the things I want to do in discovery in these cases is say, is anybody doing this? Because it's weird how little information there is.
Patrick, I think we want to make sure that get to your question.
Okay, I'll try to keep it brief. My air conditioning just came on, by the way, so maybe think about this. I do have a solar power system, but not enough to power the air conditioning by itself unless I dip into the batteries pretty deeply. I'm interested also in trying to quantify the relative benefits from some of the strategies that you mentioned, because it seems like VPPs are a collection of a lot of different things that are just based on a common principle, but they're very different, right? Yes. Things that have been around for a long time, like having a interruptible air conditioning or water heater, etc., which are, I guess, relatively low tech, you could say, and relatively inexpensive, all the way up to having a bi-directional charger on your EV, which is interesting because quantifying that depends on how often your EV is going to be parked and so forth, right? How much benefit are you going to get from it? The case studies that you mentioned seem to be large-scale commercial battery installations, right? Facilities. So that's another big piece of it. That seems to me that would be a very large piece, but also very expensive to implement. So what I'm trying to get at is, do we have any idea of the cost benefit ratio of some of these different strategies? You know, for example, putting all kinds of smart devices in your house, that has a cost, right? If everybody's going to do this. I'm glad I have battery backup for my solar power system. That came with a cost, although it also had a cost avoidance in the sense I did not buy a generator, right? So there's a lot of different things to be considered here. And I wonder which one of these, do we have a sense of which one of these gives us the biggest bang for the buck in aggregate? So which ones do we really target on? If we're going to like lobby the MPSC or the legislature or something, what are we, you know, what's the real, like, they used to say killer app for this, right? That'll get people's attention and really make the case the best way.
Yeah, and just to be clear, the examples I was showing you are not utility level storage.
Right.
Those are distributed assets across homes or across the territories. So just to clarify.
And that also reduces the need to upgrade the transmission infrastructure, right?
Exactly.
And that could be quantified. Yeah,
absolutely. And so I think there are a lot of ways to come at this problem. And I really appreciate the drive to want to quantify and find which asset is going to be the most impactful across the board. What I've seen through my experience in designing and implementing these systems is it is far the most crucial thing that we can do is create the standard of weights and measures, so then all assets can be measured against it, right? And once you have a standard of weights and measures, then you can say which asset for this location is going to have the greatest impact. Because one household might have a far greater impact from a battery or an EV versus another, which might have far greater impact from even just home insulation. And so finding the way of measuring is crucial. And quite frankly, the reason I say it's so crucial and why it must be transparent is there are tens, if not hundreds, perhaps even thousands of companies that all have bespoke ways to measure avoided energy use. And they're all right, because they're all basing their calculations on a certain set of assumptions. You can look at their assumptions, say, okay, I get it, you're all right. And most of them are all black boxes, so they're not shared. And so rather than worrying about who's the best at calculating this, we need to figure out how we're going to calculate it in one way moving forward. Because once again, you have the agreement on how you're measuring the resource, then you can start trading on it. Because given the current state of affairs, one person might calculate a very high number and one person might calculate a very low number. And then you spend an incredible amount of time and effort arguing over who's right. And that's not a very productive way to move the needle, in my mind. So if we can create that standard of weights and measures, I think it enables that next question of what's the most valuable and how can we support individuals or areas in the best way.
I guess I'd like to suggest that there's a cost to the measurement system itself.
Yep.
As I mentioned, when it comes into things like if you require smart appliances in order to measure how much you're saving, then that's a cost up front.
Well, and Patrick, this is also where in thinking about measuring systems, and I'm happy to hop on a call another time to dig deep into this, but for energy efficiency, I'm biased towards a whole building analysis where you're measuring at the smart meter. You're not measuring at an individual appliance. And so the individual appliances that you perhaps would measure would be your solar panels at your inverter and your battery at your inverter, or your car at your charger, right? But then thinking about appliances at the home, we have AMI rollout in Michigan. I believe consumers is, I think, 90-ish%, DTE 95. So we have all these smart meters that are measuring all these data, and we're not using them. And so there are systems to do whole building analysis at the meter to not only identify savings, but also to target customers and see where there are opportunities. And I think it's really important to start pushing the utilities to use those capabilities or to hire people to provide those capabilities.
Okay, final question. Stephen, go ahead.
So Nick kind of stole my thunder. I was going to ask, who do we need to bug at MPSC to do this? So I'll turn that into, I will be one of the loud rallying voices to do so, hopefully with the GLREA organization at my side. I'll be honest, I'm not very optimistic. We have a very long way to go. Just again, my comment earlier about even connecting a basic solar battery system onto the distribution grid. It's not easy. It's a major fight every single time. I get denied applications because they can't open a PDF and silly things like that. And it's really a shame, if I'm honest. Not only is it the climate change imperative and stopping burning things for future generations, but these technologies offer a better customer experience. It's affordable utility bills, resiliency during outages, owning your energy and doing what you please with it. But nonetheless, I stay hopeful. And I think to Patrick's point, kind of the killer app, or maybe that was John, they are coming. I've lived with this technology at my house, and it's better, faster, cheaper, and eventually customers win over regulators. But yes, nonetheless, I raise my hand very strongly to advocate for this in Michigan. I've got everything from boots on the ground experience that I mentioned up to studying this and knowing it intimately as an energy systems engineer. So sorry for not another question, but very passionate about this topic and just a great discussion I wanted to add to. So thank you, Richard.
Yeah, and thank you, Stephen. And I shot you my email, and my email's in the chat for everybody if you'd like to shoot me one. And Stephen, sounds like we'd have a great conversation. So drop me a line sometime. We can get coffee.
Yeah, Stephen and Nick, I put my email in the chat. I can direct you at the right people at the MPSC. That much I can do.
Yeah, I just want to make a quick comment to follow up with Stephen. I understand that we have a challenge in Michigan. I understand that the utilities are a major problem. But at the very beginning of this conversation, John Richter started off saying that Dan Scripps, the chair of the Michigan Public Service Commission, who has authority over the public utilities, he says that he is very interested in virtual power plants. So we have the chair was the one that brought it up. So we can deliver a product authored by Richard and Richter that makes sense. Then I think we have a very willing audience. So how far we can take it, unclear, but we need to take these steps because Dan Scripps asked us to. So the cup is always half full. We just got to keep pushing and keep nudging and keep organizing, and if we're tough enough and we're resilient enough, we will win. So thank you, Richard and John, for your presentations. They were excellent.
Thank you, everybody. Really appreciate your time, and thanks for having me.
Thank you.
Thank you, Richard.
Thank you.
We're expecting much of him.